Hi, my name is Sylvain Allais from Université du Québec à Chicoutimi in Canada, and in this short talk I'm going to give some highlights about a recent study we made on the profiling of websites. This work is realized in collaboration with Xavier Chamberlain-Thibault. First, what is the reasoning behind this paper? Well, we know that there is an increasing number of tools that have been created to process the output of web applications. By output, we mean the data that produces the visible results shown to the user, the DOM tree, the cascading style sheets associated to the page, and any other presentation properties directly assigned in a page, for example, through the use of client-side code. These tools can be used for multiple purposes, for example, fixing cross-browser issues or detecting responsive web design bugs. By the way, we have another paper in this conference talking about this topic, so I invite you to watch it. However, most of these tools, if not all these tools, exhibit a performance that depends on the size of the pages they process, or at least something related to their size. The reason is obvious. The larger the document you need to ingest, the more time or the more memory you need to consume in order to process it. Typically, the teams that produce tools for analyzing web documents perform some kind of experimental validation of their approaches and generally include some measurements of scalability on a sample of web pages. We cite two of these words in the slide, but we could mention many more. Therefore, it's reasonable to ask, are these samples representative of actual web pages we encounter online? Or to sum it up, what is the average size of a web page? Surprisingly, we couldn't find any reliable scientific paper providing even a hint of an answer to this question. So we decided to create a study to find out. What you're going to see in the next few minutes are some of the results we obtained on a sample of a little more than 700 websites around the world. Let us start with the methodology we followed. Our work has been divided into three main steps. First, we created a list of websites to be included in our study. The end result of this step is just a list of URLs whose pages were to be analyzed later. Second, we devised an apparatus to automatically visit these pages and perform a harvesting step of their DOM tree. More on that later. And finally, the data files generated by the harvesting step were processed in various ways. From this analysis, we can then draw a few conclusions about the site samples we studied. The website collection step was made from two sources. The first is the list of the Moz Top 500, which represents the 500 most frequented websites in the world. However, this list contains many duplicates, for example, Amazon Canada, Amazon USA, Amazon France, and so on. Once a single representative URL of each site was kept, we were down to 300 distinct websites. The list was then completed by a more informal gathering of URLs by asking individuals what are the sites they visit most often. We shall stress that this notion is orthogonal to that of a most visited website. That is, a site can be visited by lots of people but not be the site most visited by any single person. This is how we ended up with a list of 708 websites. The harvesting step is more technical. Our goal was to collect for each website both the DOM tree and information about the CSS attributes and classes assigned to each element in that tree. To this end, we created a JavaScript program which was designed to run when a page has finished loading. The script goes through the whole document tree, starting from the root, and retrieves data about a lot of features, tag names, CSS classes for each element, whether the element is visible or hidden, and structural information such as total number of elements, tree depth, or node degree. This operation was repeated on each of the 700 websites from our list. To automate this process, we used the TemperMonkey extension in Mozilla Firefox. It allows arbitrary JavaScript code to be injected in a web page after it is finished loading, which made it ideal for our harvesting process. It should be noted that this harvesting is done in an actual browser window by traversing the DOM tree as it is rendered by the browser. In other words, we did not simply download the HTML and CSS files, but really analyzed the actual tree produced by the application of CSS and possibly JavaScript to the page shown in a real browser window. The last step consisted of analyzing and visualizing the data. To do this, we used LabPal, a Java library that can automate the production of tables and plots. The harvesting step produced a set of files of 62 megabytes. We shall mention that from these 62 megabytes, some of the files corresponded to advertisement pop-ups that were loaded automatically and were not part of our original list of URLs. So instead of going through these pages one by one, we used a systematic method for filtering them out, which consisted of removing all pages with less than 5 DOM nodes or that belonged to an existing list of known ad pages. So, what did we get? First, we can use our harvested files to produce visualizations of the structure of each page. You can see an example here. Each node corresponds to a tag in the DOM tree, and each tag name is given a different color. The root of the tree is the black square you can find about 1/3 from the right. We didn't draw any conclusions from these pictures, but it could prove useful in the future to get an intuitive feeling of how pages are structured. Now, on a more numerical side, we started by answering our first question. How big is a web page? The graph on the left shows the cumulative distribution of pages based on the total size of their DOM tree. From this, we can see that about half of all pages have fewer than 700 nodes, and 90% of pages have fewer than 2,000 nodes. We also discovered a surprisingly strong fit of this data with a regression function whose equation is given in the paper. The other plot shows the distribution of websites with respect to the depth of the tree, which seems to follow a bell shape. Most of the pages have a depth between about 10 and 20 nodes. How many children nodes does an element have? This is shown in the plots on this slide. This time we found that 50% of websites have a maximum degree of 22 or less, while 90% of websites have a maximum degree of 80 or less. We also studied how nodes in a page were made invisible. It is known that in order to make elements in a page more dynamic, some of them can be loaded but not shown, only to be revealed when the user performs some action such as a click. On the left, we show the number of sites having 10% of invisible nodes, 20% of invisible nodes, and so on. We observe that this number is relatively the same for all intervals of 10%. On the right, we split all the invisible elements analyzed according to the way they were made invisible. We see that the majority of them are hidden by simply putting them outside of the viewport, using a very large positive offset or a negative position. Does the size of the DOM tree correlate with the number of distinct CSS classes we find in a document? Well, somewhat. The plot on the left shows the size of the tree plotted against the number of classes. And finally, we also analyze the size of a CSS class, or a combination of CSS classes, which corresponds to the number of elements that belong to them. We can see that in most pages, say 90%, no more than 15 elements belong to the same class combination. These results give us an overview of the size and structure of web pages, but obviously they only give a partial picture. The tables and plots are dependent on the sample of websites we use, and the structural information about pages may exhibit some variance due to cross-browser rendering differences or incompatibilities. Finally, we chose to concentrate only on the landing page of each site. There are reasons for this that we explain in the paper. We hope that this paper will be used in future works on web page analysis in order to provide a reference point that will help situate an experimental sample within a broader range of websites. A reference to our dataset is given in the paper so that researchers can also reuse these harvested pages for further study. So thank you very much for your attention, and see you later.